at least one, we now have to show that there can't be more than one. And so we say, okay, suppose f has two solutions. And we could call them, I don't know, you can call them anything you want. Maybe you can say, suppose that f of a is 0 and f of b is 0. So suppose you have some two numbers, a and b, and both of them, when you plug them into f, you get back 0. So that would be two solutions to this equation. Well, that just can't be, because this is a polynomial. Polynomials are also differentiable everywhere. And so now, since f is continuous on the interval, okay. Maybe what I should do is state what I'm trying to do. What I'm going to do is I'm going to apply Rolle's theorem. Apply Rolle's theorem to f on the interval ab. Rolle's theorem says if your function is continuous and differentiable on a certain interval, and the y values are the same at the beginning and end of that interval, and so the picture we have here is something like this. There's some number a, there's some number b, and this function is 0 on both of those, at both of those points. Well, what goes up must come down. There must be a place then where the derivative is 0, where that slope is 0. And so that's exactly what Rolle's theorem says. There must exist a c on the interval a, b, such that f prime of c is 0. Okay, what's wrong with that? Well, now when we go to actually take the derivative, we see that the derivative of this function is 5x to the fourth plus 3x squared plus 1. And, well, this term is always positive, this term is always positive, and this term is always positive. So on the one hand, we have that f prime of c is 0, but also f prime of c has to be positive because the derivative is always positive. And so this is a contradiction. And so what we did right here at this moment is we suppose that this function has two solutions. We got a contradiction. So f can't have two solutions because the supposition that it has two solutions leads to a contradiction. Well, we already showed that it has at least one, so then therefore it must have exactly one. That's it. Okay. Good. One more problem to go. Let's do that now. Okay. 84. This is pretty hard. I usually don't assign this, or, well, I used to assign it, then I stopped assigning it, then, anyway. I would have done it in class on the mean value theorem day. But here it is. Show that if the derivative is 0 for all x on some interval, then f is constant. Okay, this is, I think, hard. So prove that if the derivative of some function is 0 on some interval ab, then f is constant on ab. Okay. Okay, so this is a seemingly kind of silly problem. We know that constant functions have a derivative of 0. And so if you give me some function, and you tell me that this function is constant, so for example it just has value k everywhere, then of course the derivative is going to be 0, because this function is not changing anywhere. And alright, if you just write the function f of x equals k, we proved using the limit definition and everything that this is 0, so it seems like we're done. Okay, but that's actually not what this theorem is saying. It's not saying that constant functions have 0 derivative. That's of course obviously true. Instead what it's saying is, if the derivative is 0, then the function must be constant. And so this is our first encounter, the following situation. We know something about the derivative of a function. We know the rate at which a function is changing. And we want to conclude, based on that information, some properties of the function. So we are really now using differentiation to learn about a function. And this is the most simple possible example, so simple that it's kind of weird. What this is basically saying is, dude, if your function is not changing, or rather, if the rate at which the function is changing is 0, then your function just doesn't change. Okay, well, how are we going to do this? I think the simplest way to do this is, okay, well, first of all, it's a conditional. So to prove any conditional, we should assume that the derivative is 0 on the interval a, b. And from this assumption that the derivative is 0, we need to derive the conclusion, which is that f is constant. So down here, f is constant on the interval a, b. In other words, it has the same y value everywhere. How can we show that it has the same y value everywhere? Well, there's a couple different ways to do this, but probably the simplest way to do it is to do it by contradiction. So what I'm now going to do is I'm going to assume that f is not constant. So assume that f is not constant on the interval a, b, and this will lead to a contradiction. Therefore, it must be constant, and then we're done. Well, what does it mean to not be constant? Well, a constant function has the same y value everywhere, and so if this function is not constant, then it must have different y values somewhere. So what we can say if this function is not constant is that somewhere on the interval a, b, f has different values. For example, perhaps, let f of x1 be different than f of x2 for some x1 and x2. Okay, it's a very sort of theoretical, kind of a mathematical advanced argument going on here. Basically, what I'm saying is, it's quite simple. What I'm saying is, alright, here's my function. Here's a, and here is b. And I want to show that this function is constant. Well, if it isn't constant, then somewhere it's got to be just, different. In other words, it must have some y value here, and it's just some different y value here. So maybe that's f of x1, and that's f of x2. And now I am going to claim that this is in fact impossible. And the reason why it's impossible is because this derivative is 0, right? And so f is differentiable on the interval. Well, on the interval x1, y1. Sorry, x1, x2. And since differentiability implies continuity, if a function is differentiable, then it's definitely continuous. F is also continuous on the interval x1, x2. And so, what we're now going to do is apply the mean value theorem. So apply the mean value theorem to f on this interval x1, x2. Okay. Make these closed brackets. It doesn't really matter. Okay, so yeah. Good. What does that mean? What that means is that what does the mean value theorem say? It says that there exists some point C on the interval AB such that, maybe I'll sort of continue over here, such that the derivative of f at C, there's this special point C, such that the derivative at that point is equal to, not AB, x1, x2. I'm applying the mean value theorem to this interval from x1 to x2, where these are the 2 points where the function has different value. And there must be somewhere where the derivative at c is equal to the average rate of change. So that's f of x2 minus f of x1 over x2 minus x1. Okay, but that just can't be, because by my assumption that f1 and f of x1 and f of x2 are different from each other, that means that this numerator is not 0. And if this numerator is not 0, then it means that the derivative at c is not 0. But we know that the derivative at c has to be 0 because of our thing at the very, very top, that the derivative is 0 everywhere. Okay, this might strike you as extremely convoluted. In words, here's what this says. Look, suppose the derivative is 0 everywhere on an interval. Well, if the derivative is 0 everywhere, then you simply can't have the function experiencing any kind of change. Because if the function is experiencing any kind of change whatsoever, then on that interval on which there's change, this function will change by some amount, and so there we can talk about the average rate at which that function changes on that interval. And the mean value theorem says that if for any function which is continuous and differentiable, somewhere on this interval there is some point where the instantaneous rate of change equals the average rate of change. But we can't have an instantaneous rate of change equal to the slope of this red line because the derivative is 0 everywhere. Okay. Good. That was number 84. And if you noticed, this might make a little bit more sense now. The very next video that you had to watch, which was all about using the derivative to figure out when a function is increasing and decreasing, and the first derivative test, that I started with a follow-up comment, sort of assuming that this had been the very last thing that I had done in the previous lecture of that year. So maybe that makes a little bit more sense now. Okay, goodbye.